All right, we are now live for the Google Hangout. And I pre-entered some questions for us to go over so I don't have to miss any time. What I'm gonna do really quick though is I'm gonna go ahead and post this link into Schoology. Just say, hey, we're here as a reminder. That way that everyone will know to join. So I'm putting that in right now. Hopefully, people will join. I'm going to put it in all the classes. Bear with me for just one moment, and then I'll start reviewing. All right. I think we're good to go. Okay. So the first one on the list was equilibrium with special emphasis on problems dealing with pressure. So what I'm going to do is actually share my bamboo paper because I think that'll be easier for everyone to see. Right. All right, and so one of the reactions that I like to use for all of this is that the Haber process. So I'll just write it up here. Equilibrium. Am I spelling that right? Equilibrium. I hope so. And we're going to talk about gases first, okay? Which means we're referring to pressure. That is the factor that we're changing, okay? So looking at the Haber process, N2 plus 3H2 in equilibrium, so I have double arrows here. It's in equilibrium with 2NH3, okay? So I've tried a couple different ways of describing this. Personally, I like the one where I draw balloons and put in dots, but a student said actually I should do it just talking about coefficients. So that's what I'm gonna do. And the first one is this. So you have to add the coefficients up. There's nothing here, so that's really a 1. So on the left side of this equation, there's a total of 4 as far as the coefficient. That's 4 molecules. On the right side, we have 2. Okay, so if we have the situation, this is not the teeter-totter model, okay? This is just a straight up, like wherever the pressure pushes this reaction, that's where it goes, okay? So if we are to, let me pick a different color now, let's pick purple, I like purple. If we increase pressure, okay, we increase pressure, that's gonna make the area here get really small, okay, because we're pushing on it, pushing, 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 okay? So if we increase pressure, then that means we're gonna have a small volume because volume and pressure are inversely proportional. That means they do the opposite thing. So if there's a small volume, that means small coefficients. Okay? So increased pressure, small volume, small coefficients. If we increase pressure, it's going to be on the right side. It's going to favor the products, okay? It's going to favor it's going to go right, it's going to go forward, favor the products. Those are all phrases that we can use. Now, if we decrease pressure, decrease pressure. If we decrease pressure, then we're going to have a big volume because now it's sort of like pushing out. I'm just stuck it a bit. It's too low. Oh, yeah. Okay, there we go. All right. So that means that we now have a large volume. Large volume equals large coefficients. Right there. Okay. So this left side would be favored. The reactant side is favored. The reverse reaction is favored. So looking at this reaction right here, you would go left if you decrease pressure. Okay? You would go right if you increase pressure. That's just for this reaction. Okay? Each reaction you have to take separately. But for this reaction, you decrease pressure, it's going to go left because we want more molecules. Decrease pressure, large volume, large coefficients. Increase pressure, small volume, small coefficients. Okay? All right. That is the one piece, as far as equilibrium goes, that most students really struggle with. If they miss something, it's usually having to do with pressure. Okay? So if you can get that in your head, no teeter-totter. All you're talking about is, which side do you want to be on? Is it going to be, the pressure is going to push you one side or the other. Increase pressure, it's going to be the small side, small coefficients. Decrease pressure, the big side, the big coefficients. Okay? All right, so equilibrium, that was with gases. Now, let's do equilibrium, though, with concentration. Concentration. Okay. Same reaction. We can use the exact same reaction. N2, and we're just going to put the 1 here now. N2 plus 3H2 yields 2NH3. Okay? And when you're dealing with concentration, yes, you can absolutely have the teeter-totter. So I'm going to put the teeter-totter right here. And you have to realize that I am a horrible artist. So here's my teeter-totter. And the teeter-totter has its fulcrum where it's thing that it goes back and forth on. Okay. So what happens is wherever we increase concentration, okay? So if we increase the concentration, that's what the brackets mean, increase the concentration. If we increase the N2, increase the nitrogen, okay? That means that we now add more to this side, which means that now if we add a whole bunch of nitrogen, the teeter-totter is actually going to look like this, right? Okay? It's sort of like putting a person in there. Like, hi, I'm going to sit on this side of the teeter-totter. I'm Mr. Nitrogen. So Mr. Nitrogen sits on the side, and that side goes up. Well, how are you going to make this get back to equilibrium? Okay? And so what you're going to need to do is you're going to have to add on the right side. You got to put a person on the right side now. Okay? And so then we'll make him purple. And so now we get back to equilibrium. I might as well make a whole new. Because now we have Mr. Nitrogen on this side. And he's got a whole bunch of this stuff, whatever it is. And then we put Mr. Ammonia on this side so it can balance out. So it, I don't think this is actually helping, is it? Shifts right. It shifts right. If you increase the concentration, it's going to shift right to reestablish equilibrium. So much better if I do it in person. Being a horrible artist does not help you at all. So, but you get the idea. Whatever side's up is where it shifts towards. So that's if we increase the concentration of the nitrogen. We increase nitrogen, so we have to go right to get back to equilibrium. If we had decreased the nitrogen, then this side would have been up. Okay, that would pop. That means we would have had to go left to get back to equilibrium to balance it back out. Okay, so whichever side goes up, that's the side you have to shift towards. So if you remove something from a side, it goes up. If you remove NH3, it would go up. And then you have to shift to the right to get back to equilibrium. If you remove something from the left side, then you've got to shift left. Okay, so concentration hopefully is pretty easy. That's pretty straightforward. Let's go to temperature, because I think this one actually gives some people a little bit of a difficulty. I promise no more drawings because that was just terrible. I don't know how you guys learned anything from that if you did. Equilibrium temperature, okay? So first things first, you have to remember that endothermic heat in, it's kind of like endo. You could say endothermic. Heat in, that's endothermic, so heat's a reactant. Okay, so if I had my equation, 1N2 plus 3H2, 2NH3, I would write plus heat, because this isn't technically drawing. Technically, I'm just writing out the equation. Let's make it red so that it's a little more obvious. Plus heat. There we go. I think I had a 1 over here actually in front of this N too. Okay. So now it's heat's a reactant in an endothermic. Okay. If it's exothermic, we would say that heat exits. Okay. Heat is a product. Okay, so if we do this one more time, 1N2 plus 3H2 gives us 2NH3 plus heat. Okay, so now it's exothermic because the heat's on the right side. Heat's a product. And then the next question, once we've done that, then you just treat it just like you would concentration. You have to get this part down first. If you don't get this part down first, it could be very confusing. So if it's endothermic, we're up here. If it's endothermic heat's a reactant, and we increase the temperature. I'm gonna write here. If you increase temp, it's going to push that side down on your teeter-totter, so it's going to shift right. Okay, it's going to shift forward or to the product side, right? To the product side. Okay. If you decrease temp on an endothermic, it's going to shift left to the reactant side. Okay. On an exothermic, if you increase temp, on an exothermic, it's going to shift left, which is to the reactant side. And if, I might as well just do it right here because I'm running out of space at the bottom. If you decrease the temperature, it's like you're pulling away from that, which means the teeter-totter is going to go up on the right side. So if you decrease temp, it's going to shift right to the product side. Okay, so, and actually those are true every single time. If it's exothermic and you increase heat, it's going to shift left to the reactant side. If it's endothermic and you increase heat, it's going to shift right to the product side. That's true every single time. So you can memorize that, or just remember that you need to put heat on the left side for endothermic and on the right side for exothermic, and then treat it just like you would for concentration. So that's how you would address that essential skill. And of course, there'll be questions like that on the test. And I'm just kind of looking for them actually. Yeah. So just make sure that you understand that. And of course, some of you have that essential skill to make up anyhow. So hopefully that helps. Okay. Oops, I didn't highlight it. I should have selected it. I waited too long. So I just selected it on the Q&A app, and I'm sorry, I should have selected it to begin with. So if you're just now watching, you clicked on it because you want to go to equilibrium, you're just needing to back up a few minutes, like 10 or 15, and then you can go through that problem. So I apologize that I didn't click on it soon enough. All right, so I don't see any other questions. Nobody's put in any questions from the Q&A app right now. So please put in questions. Otherwise, I'm just going to keep going with these other topics. The second question I want to talk about, or the second topic I wanted to talk about was, will the reaction happen? Solubility Rules and Activity series. So that's the one we're going to do right now. Unless you guys put another question, I'll address that. What I'd like to do for that is actually show you this activity series and solubility rules. And here we go. Okay. So it popped up there, but it didn't pop up for me for some reason. There we go. Okay. The activity series. I'm gonna write some stuff right in here. Only single replacement reactions. Only single replacement reactions. Okay. Something else you should take in when you look at this. Elements higher on table are more reactive. Okay. So if you look at this, fluorine is much more reactive than chlorine, bromine, or iodine. And if you looked at a periodic table, fluorine would be the highest. So that's easy for the halogens. On the left side, for the metals, lithium is the most reactive. And if you look at it, it's actually higher on the table, excuse me, but it's further to the left as well. So further to the left is more reactive. That's the main thing. So lithium, potassium, you've got calcium, sodium, magnesium. And it's not about whether it's up or down so much, because I think sodium is actually above potassium. I think lithium is above sodium. Is that right? Lithium is above sodium is above potassium, but that's not how it is here. So you can't say that it is top to bottom for the metals. Just know that the further to the left, usually it's the more reactive, which is why lithium. So, and you look here, lithium, potassium, and sodium are all alkaline metals, which are extremely reactive. And then you put in some calcium and some magnesium. Also, those are alkaline earth metals, so those are pretty reactive. So let's look at some problems and see if we can identify it. Remember, these are just for single replacement reactions. So let's see, where did I put? There they are. Okay. Oops. Having some issues here. Okay. Let's take a look. Will the reaction happen? All right, so I don't know if I'm hoping you might have this in your notes and have it out in front of you, because that would make it a lot easier, because I can't share the two screens at the same time. Single replacement reactions. That's what all these are. And I think I messed up on this one, but that's okay. Let's get rid of that right now. Okay. You have aluminum, and that we're looking at number one, aluminum and lead. So what has to happen is that you have to take and look and see if the aluminum is higher than the lead. So because whatever's in the compound is the one being replaced. The one by itself is not the one being replaced. If you think back with the iron nail inside the copper nitrate, the iron nail is what fell apart. The iron seemed to come apart because the iron was leaving the nail to replace the copper in the compound. The aluminum has to be able to come in here and replace the lead in the compound, right? The dancing, right? Do you remember the single replacement reactions? And you had the, then you had the dancer comes in, like the boy replaces the boy, or the girl replaces the girl, right? It's the like replaces like. And so, but you have to replace the one in the couple, right? The one in the compound has to be replaced. So we've got to figure out, is aluminum higher on the chart than lead? Is aluminum higher on the chart than lead? So this one time, I'm going to go back to it. Then we're going to look at the rest of them and just, and then we're just going to pretend like everyone has a list that we can look at. So remember, is aluminum higher than lead? Here's aluminum. Okay. Oops, no, that's not what I want. Aluminum, is it higher than lead? And the answer is yes. Aluminum is higher than lead. Therefore, that reaction is a yes. The single replacement is higher than, or the single element is higher than the element in the compound. Okay. So I thought I would just kind of add those over here. That one's a yes. Aluminum is higher. Then we look at this one. We've got chlorine. Are we comparing chlorine and sodium? No. Chlorine is a halogen. Chlorine is a non-metal. It's to the right of the zigzag line. Sodium is a metal. It's a cation. It's to the far left of the zigzag line. So you have to have a cation replace a cation, or an anion replace an anion. And in this case, chlorine we need to see if it can replace iodine. So we look and we say, okay, we look at our activity series. Is chlorine higher than iodine on the activity series for halogens? And the answer is yes. Okay. Let's look at the next one. Aluminum and copper. Okay, is aluminum higher than copper? This single aluminum higher than copper, because we can't pair chlorine or cation to cation. Aluminum's going to form a cation. Copper's going to form a cation. Okay. And what do you think? Yes. Okay. Copper is actually fairly not reactive. The iron nail lab is a great example. When you put copper wire in iron sulfate, it does not replace the iron in the iron sulfate. Copper is actually below hydrogen. Copper, mercury, silver, platinum, gold, very non-reactive elements. Okay. Now we've got bromine, number 5. I'll give you a second to think about it. It's bromine and iodine. Bromine is higher than iodine. The answer is yes. That's a lot of yeses. That one, I don't want that to be subscript. Okay. Next one. We've got aluminum. Wow, lots of aluminums. Aluminum's and hydrochloric acid. So the aluminum, is it going to replace the chlorine or the hydrogen? Which one is a cation? The other way you can look at this is say, okay, is the single element on the left, is the single element on the left higher than the single element on the right? Because that is the way you can identify the like equations. Like has to replace like. Aluminum and copper, both cations. Bromine and iodine, both anions. Aluminum and hydrogen, both cations. And in this case, yes, it's higher. Okay. Magnesium and hydrogen. Okay, magnesium and hydrogen, they're both cations. The answer is yes. Zinc, we've got zinc and hydrogen's the one over here. So the question is, what do you zinc? Ha ha ha. Okay, so not very funny, but I thought it was well timed. Okay, the answer is zinc higher than hydrogen? Yes. Wow, they look like they're all going to be yes. Iron and copper sulfate. Hey, that's a quinky dink, just like the lab. So what's the answer? Is iron higher than copper because they're both single elements, they're both cations? And the answer is, or survey says, yes. Okay. Perfect. Perfect, perfect, perfect. Okay. So those are the activity series. Okay, there'll be a few questions like that. Sorry, I had to jot myself a note for later on. Okay, double replacement. So now let's share the solubility rules again. Now, I just want you to know I'm focusing on the things that I believe that students struggle with the most. If there's anything else, of course, that you're struggling with, you should put that question up there. But I will, and I'll hit some of the highlights when we go back. But those are the things that are newer that you're struggling with. So, solubility rules. All right, there we go. Solubility rules. Now, and I think I did this once before, I think, but let's do it again. The left side, these are all rules. The left side are rules. Here, I'm gonna, and since this isn't a real one, I'm gonna just, how can I insert, I don't wanna insert a table. I just wanna insert a row above this. How do I do that? Maybe this is it. Delete above, no. Oh, there we go, excellent. These are the rules. So, let me center that up and we'll make it a little bit larger and we'll change it to red and we'll make the whole thing yellow. Okay, so those are rules. In the same way, the rules are in that column. So, which means that one above, the same thing applies for this row right here. Okay. Send that. Okay, that means that this side, they're not rules, they're exceptions. Okay, so let me copy and paste that down here. Okay, so the rules are all in the left column, the exceptions are all on the right. So you always want to look at the left side first because those are your rules. Those are like, okay, is this true? And then if it's true, then you look over here for an exception that could make it not true. Now, all of these things right here, if you have a compound, now these are, by the way, these are also just for double replacement reactions. And you're only looking at the products. You're only looking at the products. That's very important. It's underlined, italicized, only looking at the products, okay? So the rules, if you're looking at the products and the compounds and you see one of these ions, the rule says that they are a no, okay? That they would be a no. So we're going to give it a, the no's are gonna be red. Like basically, these are all no's over here. The rules say no to those ones, okay? However, if one of the rules, like these bottom three, are paired with one of these other ions, so these ions are, the ions on the left and the rules are a no, the ions on the right are the exceptions, which would make it a yes. So I'm gonna make these a green, okay? All right, so this is the no column. This is the yes column, okay? Now, that gets flipped over here because yes column means yes to a solid because that's what we're looking for. Let me back that up a little bit. Yes to a solid. No column. That didn't work very well. No to a solid. Okay? That's really what we're asking. Did a solid get formed? That's what we really care about. Insoluble means that a solid is formed. Insoluble means that a solid is formed. That's why these two columns are the green. These rules, if you have one of these ions in your compound, the rules say, yes, this is going to form a solid. Flip these over. That's what it would say. Okay. Over here, though, the solubles means it dissolves in water. Okay. This is all the no. These are all no. Alkali metals and ammonium. Here are your alkali metals up here, and here's ammonia. Ammonium, that's NH4 plus. Okay. So this is the no column. No to a solid. Okay, that's what this column. So you can see they're kind of diagonal from each other. So when you look at it, you have to look for one of the ions in the compound. And if in the rules section first, one of these rules sections, you find it. If you don't find it, then you can look at the exceptions. But most of the time, when we give you these, it's going to be one of these in this column, one of these two columns. Okay. All right. I'm going to go share the other document again, but we're not going to come back and forth to the rules because that is tedious. So will the reaction happen? Let's look at some double replacement reactions. Okay. So they're the double replacement reactions. So we're looking at just the products. Okay. So you look at K2SO4. Well, there's a K there. That K is an alkali metal. So that right there, that compound is a no. But if we get even one yes, the whole thing's a yes. So I have to look at both of them. H2O. So the question for H2O is always, hey, is H2O, is water soluble in water? And that sounds kind of silly because obviously, yes. So you can't say that it's going to form a solid because it's not. So this one's a no because there's no solid. No solid is formed. Okay. Let's look at the next one. We've got iron chloride. So do we find Fe in our rules anywhere? And we don't see Fe in the rules anywhere. So then we look and we say, okay, is chloride in our rules? And there it is. Chloride, bromide, iodide. Is iron an exception to chloride? No, it's not. So if iron chloride is soluble, okay, so that one is a no. It's not going to form solid. And then H2S. So we're going to look for sulfide. We find sulfide in the rules down in the insoluble category. And the question then is hydrogen an exception for sulfides? Is it an alkali metal or ammonium? And the answer is no, it's not an exception. So yes, solid formed. Okay, so that means that specifically because of that one right there. Okay, let's do it again. Sodium sulfate. Sodium, alkali metal, it means that no. And hydrochloric acid, HCl. Well, it's a chloride, and hydrogen is not an exception to that. So no solid. Let's try the next one. Silver chloride. Chloride. Chloride is a rule that says that no. Is silver an exception? Yes, silver is an exception. So we don't even have to look at the other one. That's a yes right there. Yes, solid formed. Okay, good. All right, calcium phosphate. We look up phosphates. Phosphates are a rule saying that a solid is formed. Is calcium the exception? No, because calcium is not an alkali ammonium or metal. Alkali metal or ammonium. So this is interesting. On the last one, we had yes, the reaction would happen every single time, and this one seems to be going back and forth. Yes, I'm just gonna put yes or no. All right, next one, potassium chloride. Potassium is an alkali metal, so that's a no. Chlorides are no's. Carbonates. Carbonates are a yes. Is barium an exception? No. So it stays as a yes. So we give a yes. Wow, we're actually having a lot of yeses right now. I'm gonna pick this up a little bit. Oops. Oh my goodness, I can't seem to. Yes, okay. We've got cadmium sulfate. You can look it up. That's a yes. This would be kind of good if you were to kind of freeze it. If you just want to freeze the screen for a second or pause the video if you're watching it later and see if you can figure out the last ones because I'm going to answer them all. Okay. And I'll just do it real quick. No. I'll at least highlight the ones that make it yes. Yes. You guys will start to see a pattern. Sometimes practice is like overly repetitive. But I would have to say that it can be very helpful. At least I think I'm trying to move a little fast, so hopefully I'm not moving too fast. Sulfates, chromium is not an exception. Oh, interesting. I believe that one makes it a yes, because it's SO2. But it would say if it was a gas, but it doesn't say anything, so I'm assuming it's going to form either to dissolve or form a solid. And sulfur dioxide should form a solid then because it's an oxide. All right, look at the price. We've got silver chromate and potassium acetate. And the silver chromate definitely forms a solid. So there's your last one. So hopefully that helped you. And those are your solubility rules and activity series. Whew. All right. Essential skill, or I'm sorry, review topic number 3 is the other essential skills of balancing equations and reaction times. So I'm going to minimize the other windows, and I need to bring up balancing equations. All right. Share that screen. All right. So, so we look at these. Now, what I would suggest, again, if you're watching this later, is that you freeze the screen. I'm just gonna put these like this. So you just freeze the screen right now, and then you go through and try to, like 1 through 15, you try to balance those equations. Pick a few, say you're doing, because I'm about to show you all the answers in one shot. Okay, and then I can talk about them as I go through them. You froze the screen? Now? Okay, now hopefully you unfroze the screen and look here, 1 through 15. And we can see it. The very first one is one of my favorites, which we already did, is the Haber process, and then, or Haber process, it's ammonia. So there's that. So that one, I've done it so many times, I don't think it needs explanation. For number 2, the key to this one is that there are 3 oxygens on the left and 2 oxygens on the right. So you've got to get them to both to be 6, which is why you've got the 2 and the 3. And once you've done that, and the 2 KCLs and 2 KCLs, you're done. Here, pretty easy. There's an F2 right here, so you got to put 2 Fs right there. There's 2 Cls here, so you got to put a 2 over here. Okay, and that means the 2 NAs get 2 as well. The water one, we've done that one over and over again, right? You've got 2 oxygens on the left, you've got to get 2 oxygens on the right. That means you have 4 hydrogens, so you put a 2 up in front of that. Here's one of those fun ones, okay? So we have a water on one side, and you have H and OH on the other. So if you do that, you can cross out the H2O and turn it into HOH, okay? So once you do that, then you just balance the H's and OH's. There's 1 PB, 1 PB. There's 2 OH's, so then you put the 2 out in front over here. That means you have 2 OH's, and you have to then put the 2 in front of here to make sure you have 2 H's. 2 Cls, and there are 2 Cls. So pretty straightforward, but it's helpful. It makes it a lot easier. And remember, we are not only balancing that way so that the H's and the OH's are separate, but I would also say that you're balancing by polyatomic ion, which plays in very nicely to number 6. It's huge. How easy is it to say SO4 is 1 unit? There are 3 SO4s over here. So I have to put a 3 out in front for these 3 SO4s, okay? That gives me 6 of the K2s, so I have to put a 6 over here in front of these Ks. I'm sorry, there are 3 K2s, which gives me 6 Ks. I've got to put a 6 over here. That leaves me with this BR3. I got to put a 2 out in front of that, and it gives me 6 BRs. So that's how I end up balancing that. The 7, 8, and 9 are all combustion reactions. They're a little bit more difficult to do, but we will not give you something as difficult. not even close to something as difficult as number 9. It's not impossible. You can do it, but just realize that if you're struggling with it, if it's taking a long time, don't worry about it. You won't have anything like it. Okay, so you'll have something like 7 for sure, and then 8. I don't know if we're gonna go I don't think it's like that. It doesn't go that bad. The balancing is actually pretty easy, pretty straightforward. Let me just double check. It's actually really easy. I don't see it'll be. So let's look at number. They're all so easy. Nothing like 15. I would focus primarily on 1 through. If you can do 1 through 7, you should be just fine. We've done one like number 11 too. Doesn't happen very often. One like number 12. So 1 through 7, 11, 12, something like that. Anyways, okay. So those are the balancing equations. And I think that makes enough sense. The next one, though, is the reaction types. Okay, the reaction types. And actually, it doesn't matter if they're balanced or not, because if we give it to you, sometimes they'll be balanced, sometimes not. Sometimes we'll use generic formulas. Okay, so actually, why don't I do that right now? I'm going to do some generic formulas, and then we'll come back and use the balancing equations worksheet to try to pick the reaction types. Okay. So I just selected the question for balancing equations and reaction types. So if you want to see the balancing equation stuff, you need to back up like 10 minutes. Sorry, I keep hitting the questions late. All right, so I'm going to share my Bamboo tablet again. We'll talk about the reaction types. Okay, pick a new page. And the first thing, you should be able to do it, just the generic stuff. So if we have A plus B yields C, of course, this is synthesis. Okay, and the opposite of this is if you go, C goes to, actually, you know what? I shouldn't do it like that. I should make it really obvious where it all comes from. Sorry, A plus B yields AB. That's synthesis. If you had AB goes to A plus B, that's decomposition. Decomposition, okay? And you could also have something like, you could have ABC goes to AB plus C. That's also decomp. So don't be fooled by the fact that sometimes you have a compound and an element come together to form something bigger, or something bigger breaks down into a compound and an element. All right, A plus BX yields AX plus B. This is single replacement. You have a single element here on the left side, a single element on the right side, and 2 compounds. It just replaced one of the elements and kicked it out. Remember, like replaces like. Then we have AX plus BY. You have AY plus BX. Okay, so basically your cations switch places. Okay, so I think that's pretty straightforward. And my way to remember this, I try to tell you guys, is that it just goes on and on for days. There's compound plus yields compound plus compound. Okay, there's no single elements anywhere in that. It's it is the only reaction type with no single elements. Every other reaction type has a single element somewhere in there, but not double replacement. Okay, and finally, CXHY plus O2 yields CO2 plus H2O. Okay, and this one's combustion, the last one. The last 3 things in the reaction are always the same. It's always plus oxygen yields carbon dioxide plus water. Always the same. Okay? That's how it rolls. Always the same. So those are the 5 reaction types. So let's go back to the balancing equation and see if we can identify some of the reactions. Okay, so the first one, you have a single element plus a single element yields a compound. Synthesis, good. You have a compound yields a compound plus a single element. Well, you've got 2 things breaking down from 1, decomposition. Number 3, you have a compound and a single element as reactants. And on the product side, you have a single element plus a compound. That is most definitely a single replacement. Number 4, 2 things come together from 1, synthesis. Number 5, it is the longest equation here. Look at this. Look at how far to the right it goes. It is most definitely double replacement, okay? Look at all the ones that go really far. Here we go, number 5, double replacement. Number 6, double replacement. Number 10, double replacement. There's no single elements anywhere in that, okay? And then you say, well, look at number 9. That goes on a long ways. Okay, look at number 9. Is there a single element in there? Yes, the O2 is a single element. It cannot be a double replacement if you have even 1 single element. So you look at this, and oh, that looks familiar. O2 yields CO2 plus H2O. That is combustion. O2 yields CO2 plus H2O. Combustion. O2 yields CO2 plus H2O. Combustion. Over and over again. Number 15. Oh, number 15 is the reverse, right? You should recognize number 15. That is a respiration, right? Photosynthesis would be that sugar plus oxygen yields carbon dioxide and water. This is respiration, or I think that's right. I'm getting it backwards. I haven't taught biology in so long. I'm totally messing this up, I'm sure. But anyways, it's the reverse of a combustion reaction. So those are your reaction types, and hopefully that was good practice for you. All right, the last topic that I wanted to emphasize was translating equations and predicting products, because I feel like a lot of people struggled with that. It was on the free response, and it is not that difficult, but I guess I'm the teacher, so what do I know, right? It involves swap and drop, which you had done from the last unit. So let's bring up a page and take a look at it. Okay, let me take a little sip. Okay, so for this one, actually, give me a second. I'm going to do something real quick. If you forgive me for a moment, I'm going to bring it down off the screen. And on one of these, or 2 of them, wait, okay, sorry. I wanted to have you predict products as well as translating. Okay. Let's go back to that screen. Okay, writing equations. So it says when dissolved beryllium chloride, right? So you have to look those up on your periodic table. You look it up and you say, okay, beryllium, Be, and it's in the second column, so it's a 2+. And chloride, it's a Cl, and you determine its charge. Now this is something we've been doing all year. I don't want to have to go back and do this over and over again, so I'm gonna do it once for you guys. Beryllium is in the second column. It has 2 valence electrons. Is it easier for it to gain 6 or lose the 2? And it's going to want to lose the 2 to get down to 8. Remember, we said 4 is kind of our middle ground. If it's got above 4, it's going to gain more to get to 8. If it has less than 4, it's going to lose those to get to 8. So beryllium is going to form a +2. In addition, it's also to the left of the zigzag line, which it's definitely going to be positive if that happens, okay? So beryllium 2+, chlorine is 7 electrons. It needs 1 more to get to 8. It really wants to pull that 1 more to get to 8. it's much energetically, it's easier to do that than it is to lose 7 electrons to get down to the next lowest level of 8. So once you do swap and drop, you swap and drop the 2 and the 1 that's not written there, but it's understood. So when you do that, you end up with BeCl2, and the 2 is a subscript on the chloride. Okay, so when you get these, you need to do swap and drop to get the final, or not the final, but get the formula for the word. Okay, so silver nitrate. So Ag, and if you remember, I said silver, Ag is always a 1+. Silver is always 1+, just like aluminum is always a 3+, and zinc is always a 2+. So you've got silver and nitrate. Nitrate's not an element. The 8 gives it away. If it ends in IDE, it is an element. If it ends in like ATE or ITE, that's the clue that it's a polyatomic ion. So I'm going to put these, because polyatomic ions, you should get used to just putting in parentheses so that you don't get totally faked out. So it's NO3, 1-. This one's actually a pretty easy one. You just put them together. Ag, I don't know. You don't have to use parentheses for this. I just am because I want you guys to be able to recognize when you see a polyatomic ion. Okay. So these are coming together. Maybe I'll put this a little closer. Oops. Okay. Oops. Too far. They combine, it tells you what it does. But if you had to predict the products, you would say, oh, if we ask you to predict products, we are only ever going to ask you to predict for a double replacement or a single replacement reaction. Okay, it's only one of those two. And if it's a single replacement reaction, one of your reactants has to be a single element. So here, there's 2 compounds. So basically your Ag and your Be are going to switch places. So you're going to left with AgCl plus Be NO3 and with the 2 outside of it. Because beryllium's a 2+ and nitrate is a 1-. Okay? And then you balance it, which I think should be pretty straightforward. I think you're just going to end up putting a 2 over there and a 2 over there, and you're finished. Right? Let's skip number 2. Let's go to number 3. When dissolved sodium hydroxide reacts with sulfuric acid. And they gave you the formula for sulfuric acid, which was really nice, of course. But you guys need to memorize your acids. There are 6 acids. You need to memorize them. We'll talk about them in a second, or I'll type them up here in a second. Sodium hydroxide, NaOH. Because the OH is even though it ends in IDE, there is no such element as hydroxygen or hydroxine or something like that. Hydroxide is a polyatomic ion. You didn't know that one. It's on the back of your periodic table. It's a 1-, sodium's a 1+, so you end up with an NaOH. Sulfuric acid is an H2, so well, it's right there for you. So hopefully you have it memorized. I'm just going to put it right here. Okay. And when these 2 combine, this is a double replacement, so we know the Na and the H are going to switch places. So you end up with an HOH plus Na2SO4. SO4 is sulfate, it's a polyatomic ion. It has a 2-. So when it pairs with sodium, which is a 1+, you get Na2SO4. And since the H was placed with the HOH, you've got HOH, which you should also be familiar with that enough now that you recognize that as H2O. There's different ways of saying the same thing. All right, the next one. It tells you what it is, but fluorine is put into contact with calcium metal. Oops. That's calcium metal at high temperatures. Okay. Gives you calcium 2+ with fluoride 1- F2. So this was not a predict product. It tells you what it is. Okay, so you look at it, you're like, oh, great. I can just put a 2 out in front of this, and I'd be done. Except when you see a single element, you should think to yourself, single elements are, if I get single elements, are they diatomic? The only way I'll know if they're diatomic is if they are Brinkelhoff. 2, I2, N2, Cl2, H2, O2, F2. That's Brinkelhoff. So what I'm gonna do is I'm gonna highlight all these 2's to make them subscripts, and you can see there's 7 of them, and they're highlighted yellow on my periodic table on the wall. So I guess that would be one way of cheating, or not really, but it's because it's there for you. But it's, anyways, try to memorize it if you can. There's Brinkelhoff. Is F a part of Brinkelhoff? Yes. So what we need to do is remove that 2 because we don't really need it, and you need the 2 as a subscript. All right. All right, and then finally, our last one for translating and balancing and predicting products is sodium, just sodium metal. Is it a part of Brinkelhoff? No, it's not one of the 7. Fe with iron is an Fe. The 2 there tells you the charge on the iron. So the Fe 2 plus, and the chloride is a 1 minus. So I'm just gonna make those superscripts. That's just super. And when you do swap and drop, you end up with FeCl2, because the 2 comes down from the iron to the subscript on the Cl. All right. And remember that the only ones we're making you predict the products are double replacements and single replacements. This is a single replacement because the Na is 1. So, oops. The Na is going to want to, we're writing it out. We're predicting the products. Whether it actually happens or not is a different conversation. But just predicting the products, Na would be a single replacement on a like element, something else that's going to form a cation. In this case, it's going to be iron. So you end up with NaCl plus Fe. Right? And you still need to balance it. So you got to put a 2 out here in front of the NaCl so that you're got 2 Cl's, and then a 2 in front of the Na. And that is your answer. You translated it, you predicted products, you balanced it, all those things, and neither iron nor sodium is part of Brinkelhoff, so you're good to go. So if we looked, let's look at, so these 4 and 5, well, you could probably look at all of them, and you did it. Yay, team. Did we put a 2 in front? Yeah, we did. Yay, team. Okay. All right, so that's that topic. We only have a couple minutes left. No other questions have been posted, unfortunate. So let me just bring up the bamboo paper and a couple last things that you should be memorizing. So we'll call these hot tips. Okay. Brinkelhoff. Six acids. Is it 6 acids? Can't remember. We've got HCl. We've got H hydrobromic acid, hydroiodic acid, which are the halogens, and then the oxy acids, which are nitric acid, HNO3, sulfuric acid, oops, that's not an H. Who wrote that? Sulfuric acid, H2SO4, and perchloric acid, HClO4. So I'm kind of hoping, I can't remember, I don't have the notes right in front of me, but I believe those are the 6 acids that you're going to need to know about. Make sure you memorize those. Make sure, you're obviously all of the essential skills and the rules for balancing equations and writing reaction types and things. Gosh, I feel like I've covered it all. Maybe definitions. definitions would be a good one. And I would encourage you to review all reactions in this Hangout, because several of those videos, not the exact equation, but several of those equations in this video are going to be very similar to things you're going to see on the test. So if you have time to go back through, those are things I would recommend. But definitely, I mean, I think I hit all the things that are important, or are that, I mean, this really, I tried to relate this really closely to the test. So if you've been paying attention, if you've gone through these things, oh, last thing I would recommend, actually, let me see if I can share it with you too. For more practice, to double check, to make sure you are doing it well, let's do the, not the entire screen. Hold on one second. I see what the problem is. I need to bring up my, let's try this again. Okay. There we go. Okay. I cannot emphasize this enough. You need to go to ScienceGeek, ScienceGeek.net. And I typed in my book, my search bar. I go to ScienceGeek.net, I click on chemistry. I click on review. And then here are a bunch of quizzes. So I look for the things that are similar to what we're doing right now. And I keep going down. There's equation balancing, if you need to go back to that. Reaction energy and kinetics. So actually, that's kind of interesting because that's what we're going to be doing next. Oh, maybe I already passed it. I think I went too fast. Oh, predicting the names of products. Does this reaction occur? Oh, look at that. Identifying the reaction type. This is great stuff. So does this reaction occur? Unit 4, conservation of matter. So you look at it and you say, okay, I want to see all the questions at once. Silver plus sulfuric acid gives you silver sulfate plus hydrogen gas. And you say, okay, does Ag, which is going to replace the cation or the anion? Well, it forms a cation. It's going to replace the hydrogen. You can look over here. Will silver, the single element on this side, replace hydrogen, the single element on that side? And the question is it higher on the activity series? The answer is no. Okay. And so I click right there. Yes, yay for us. Okay. So that's what you should do. Oh, interesting. Anyways, answer his questions over here. This is how we're doing it. So you can do those. I would say this though. This is interesting. He said, if it produces gas, water, or a precipitate, it's a yes, which I think is fine. Using the water one, that actually can be a yes, but we're not doing that. So ignore that. But if it comes up one of the problems and you're not sure, don't worry about it, okay? Just try to follow our rules and you'll be fine. So that's the last piece I wanted to say. I hope that you gained something out of this tonight. And if you're taking the test on Friday, good luck. If I'm taking the test on Monday, you still have some time. You can ask me questions or email or on Schoology or come in and visit me. Either way, I'll try to be very responsive. I'll try to, as soon as I get the message, I'll try to get back to you. I want you guys to do well on this, all right? Anyways, I'll just double check. I don't see any questions, so I think we're finished. All right, thanks guys. Good night.